For our final application of the derivative, we're going to see how we can use what we know about the derivative to optimize functions, meaning to find maximum and minimum values of a function. So here we're going to look at not just general functions, but functions that measure something useful. And we're going to use calculus to find maximum or minimum values. Now, we've seen this before in some context when we covered the extreme value theorem last week. We saw when we had a closed and bounded interval, we could find a maximum and we could find a minimum that a function achieves, if it's continuous, on that interval. Now, here, we could have some questions where you can find a closed and bounded domain and apply the extreme value theorem. We're going to look at slightly different examples which look more like these curves, and essentially they will go off to infinity. But we are going to show when we get a maximum versus a minimum. Now, how can we describe this using calculus? Well, we're going to see there are two ways. So notice we may conclude a critical point. We have critical points here because the derivative at these x values for each of these curves is 0. And of course it could be a corner at the top instead of a rounded off mound. But notice we may conclude a critical point gives a maximum or a minimum using the first derivative. What would the first derivative tell us? Well, using the first derivative, we can conclude we have a maximum if we show using the first derivative that the curve is increasing to the left of x and decreasing to the right. And we can use the first derivative to show that. Show the first derivative is what? Positive here, negative here. If you do that, then the critical point will correspond to a maximum. And similarly, using the first derivative, if the first derivative is negative on the left of x, positive on the right, it'll go from decreasing to increasing, and the critical point will give you a minimum. Now, doing that, there are some functions where the calculus works so that that does become more convenient. Well, at least most of the functions we will cover, most of the applications we will cover, using a second derivative may be simpler. You can see I initially wanted to put 1 here, and I would have put 2 here, but I wanted them on the same board, so colon 1, 2. Now why can we use a second derivative observation? Well, these curves differ also in concavity. Let's get rid of these words. These curves differ in concavity. This one is concave down through x. This one is concave up through x. So if we have a critical point and we show that the curve is concave down through that x value, then we will have a maximum. How did I phrase it in my notes? Yeah, okay, I like that phrasing more than what I was about to write. If but in practicing, using the second derivative may be simpler, okay. If a maximum occurs at x, then f prime prime at that x value concave down. So when we were doing graphs, we had some calculus results which also manifested themselves in convenient language results. Meaning, we had first derivative positive, increasing, second derivative positive, concave up. We had positive, increasing, and up, all going together. So right here, you might think, well, the positive sounding word here is maximum, so you might think positive. But in fact, if you go to this curve, we have that it's concave down. So in all of these examples, when we use the second derivative, I always draw one of these curves because this result, the language doesn't really work out as nicely as it did when we were doing graphing. More on that when we go through the examples. If a maximum occurs at f, then f prime second prime at x is greater than less than 0. I'm going to phrase that slightly differently. F prime prime is negative. I'm going to say at x to make it clear that what we're doing is we'll find that the second derivative is negative at that x value. And similarly, that's described by that first curve. Similarly, if a minimum occurs at x, then f prime prime. If a minimum occurs, we have concave up, so the second derivative is positive at x. So we could use those first derivative observations. We could use one of these second derivative observations. So let's do a few examples. In these examples, we are going to have to set up our equations because we're describing a situation with we're describing a mathematical situation with words. Let's do this one. With this one, I will show both of these ways we could conclude the maximum. The sum of two numbers is 16. Minimize the sum of their squares. Let's write that over here. Example. The sum of two numbers is 16. Minimize the sum of their squares. So with this, we are going to have to set up an equation, possibly two equations. In this example, two equations. In some examples, maybe one equation. And to come up with our equation, we're going to need some variables. So the first sentence says the sum of two numbers is 16. Great. So this is the end of the exam. I guess I'll write the equations here. This question probably won't take all the boards. Yeah, I don't think it will. The sum of two numbers is 16. Well, let's pick two numbers. We do calculus mostly with x's and y's. There's one equation. An equation with two variables. But we're not doing calculus on that equation. We're doing calculus on the function we want to optimize, on the function we want to maximize or minimize. This is just a relation between the variables. Minimize the sum of their squares. What is the sum of their squares? Well, sum of their squares, I'm going to write that a little lower. I'm going to write this on the first word. Actually, I forgot about that one step I'll need. End of example. First equation, we have x plus y equals 16. Next equation, we have x squared plus y squared. This is the function we are minimizing, so this is the function we're doing calculus on. I'm going to call it a letter. I'll call it capital S, because eventually I'm going to need an S prime, so I'll just call it an S. And right at this stage, I always like to make a mark or just write down which function we're doing calculus on, meaning which function we're optimizing. So here, we're doing calculus on this function down here, x squared plus y squared. But notice, this is a function of two variables. Our calculus is in one variable. How can we eliminate one of the variables? Well, we have this nice relation. So let's use that relation. I like taking derivatives with x's. Derivative of 4x squared with respect to x is 8x. Derivative of 4y squared with respect to y is 8y. They're technically the same, but it feels more... I'm more comfortable dealing with x's when I can. So I'm going to eliminate y. S equals x squared plus y squared. What is y? Y is 16 minus x. Solve that for y, 16 minus x. Replace y with 16 minus x. And here's our equation S that we're doing calculus on, just in terms of x. Now let's simplify that square, because this one will be easier if we just write it directly as the polynomial instead of some strange factored form. 16 and 16, 256, negative 32x, positive x squared. Equals x squared, positive 256. You could write that as 16 squared if you want. Its derivative is 0, so it's not going to really matter. So square everything there, and just combine the like terms. And we have 2x squared plus a negative 32x plus 256. And right here, the function we're doing calculus on is now just a polynomial. What are we going to do? Well, we need to show one of these occurs. So we're first going to need the critical points, where the derivative is 0, where the derivative is undefined. So let's find the critical points. I'm going to do that on this board. What's S prime? Well, 4x minus 32. We need to set this equal to 0. 8 times 4 is 32. So this is 0 when x equals 8. So now we need to show that this does in fact give a minimum. Well, and then we have to actually find what we want to find. So let's first show x equals 8 gives a minimum. And as mentioned before, there are two ways we could do this. We could do a concavity observation, or we can do a decreasing to increasing observation. I'll show you both for this one. For the rest of the examples, I'll use just the second derivative. I'll say there are two ways to show x equals 8 gives a minimum. Way 1. Now these 1 and 2 don't correspond to the 1 and 2 that were over here. Those 1 and 2 were were second derivative observations. So instead of just saying 1, 2, I'm going to say way 1, way 2. Way 1, I will use first derivative. And how can we use the first derivative to reach the conclusion that it gives a minimum? Well, we use the first derivative test. We need it to be, what? Decreasing into increasing. So let's evaluate the derivative at a number to the left of 8. A number to the left of 8, how about 7? Is that eraser going to stay? It is. What's S prime at 7? Negative 4. So S prime is negative. What about the right of 8? What's S prime on the right of 8? Well, S prime at 9 is a positive 4, so S prime on the right of 8 is positive. So that tells us that the original S function goes from decreasing to increasing, which looks like that. So x equals 8 gives a minimum. So there's one way using the first derivative. This example, this computation, these two computations were pretty easy compared to some of the later examples we do. But what would way 2 be? Way 2 using second derivative. Well, what does that tell us? Well, it tells us if we show the function is concave up through 8, then we have a minimum. So S prime prime equals what? 4 equals 4. It's always 4, which is always positive, but in particular it's positive when x equals 8. That tells us that S is concave up. So our critical point will give a minimum. So x equals 8 gives a minimum. So either way you want, you can use. You certainly don't have to show both ways. So we've shown x equals 8 gives a minimum. Is that what the question says to do? Minimize the sum of their squares. Well, it's not. We need to minimize the sum of their squares. So what is the smallest sum of squares? Well, then s equals what? Well, we need to substitute x equals 8. So you could go through, you could find y, you get y equals 8, s equals 8 squared plus a squared equals 128. Or you could use this equation where you don't have any more y's. So I'll just say s of 8 equals 8 squared plus 16 minus 8 squared, that's a plus, equals 64 plus 64 equals 128. And what's 128? The minimum sum. So I'll just say is the minimum sum. And why is it the minimum? Well, we know that when x equals 8, it gives the minimum. And we used calculus to show that. So this last conclusion would have to follow either process you went through. Now, unless it just says what x value minimizes the sum. We'll see probably one or two like that. Let's look at another couple examples. Example. A farmer has 2,400 feet of fencing and wants to enclose a rectangular field that borders a straight river, and that side will not require any fencing, the side bordering the river. What dimensions maximize the area? So down here, this last sentence does tell us what we're eventually going to need to do calculus on, but it may be helpful here to draw a picture. Farmer, 2,400 feet of fencing, wants to enclose a rectangular field that borders a straight. Well, I have a blue marker, so let's make the river blue. That makes sense, I guess. Let's put the river down here. Straight river. Let's make it that straight. So there's the river, and here's the fencing. And now it kind of looks like a half rest node. So there's the fencing. We know that those three sides of fencing are going to have to add to 2,400, but it's rectangular, so this side and this side are the same, so let's call those two x, and let's call the other one y. So now we have a diagram from which we can find a couple equations. First, well, what are we doing calculus on? Well, let's write the other one first. First, we have 2,400 feet of fencing. So 2x plus y must equal 2,400. And we want to maximize the area. So we're doing calculus on the area function, a, which equals x, y. Now, well, again, as in the previous example, the area function is now a function of two variables. But what we can do is use this constraint to eliminate a variable, because y equals 2,400 minus 2x. So I'll just write down here, equals x, and I won't write it down there. I won't have room on the next line. So a equals x, y equals x times 2,400 minus 2x. So y equals 2,400 minus 2x. Replace y with 2,400 minus 2x. And now we'll just distribute that because we don't have any product rules to look at. 2,400x minus 2x squared. And we want to do calculus on this. Well, we'll proceed as before. Find the critical points. In these, if they're polynomials, there aren't going to be any points where the derivative is undefined, so you don't even have to think about that. If they're not polynomials, which we will see an example like that, then you might have to consider where the derivative is undefined. But the derivative here, 2,400 minus 4x, we'll set it equal to 0. Why I mention it being undefined, well, technically you'd have to say equals 0 when x equals 600 and is never undefined. But with a polynomial, don't worry about that. It is never undefined. That's, too much writing for what it's worth. In the examples where an undefined point will occur, it'll be obvious because we'll have fractions. But we need to show that this gives a maximum for the area. How can we show it gives a maximum? Well, let's just do it like this. You could do a first derivative observation. With this one, it wouldn't be too bad because you get increasing and then decreasing. At 500, the derivative is positive. At 700, it's negative, giving a maximum. But I'll just say x equals 600. Well, I won't even write it like that. I'll say it like this. A prime prime equals what? Negative 4, which is negative when x equals 600. So x equals 600. I'm going to move so down a little bit. So x equals 600 does in fact, what happens when the second derivative is negative? Well, it's concave down. So our critical point will be up, our critical x value will correspond to a point up there corresponding to a maximum. So x equals 600 gives a maximum. Now, why did I write that so out of line? Well, I don't believe there was an earthquake in the middle of my sentence, although there may have been. What does the question ask? What dimensions maximize the area? Well, what dimensions tell us we need an x and a y? We don't need the maximum area. This maximum area would wind up being 720,000, which I know because I wrote it over there. But this question says what dimensions? So once you do all of this calculus, it's always good to go back and be sure you're answering the question that's being asked. Here we need an x and a y. X equals 600, y equals what? Constraint, let x equal 600. 1200 plus y is 2400, y is 1200. So x equals 600, y equals 1200 gives a maximum. If it did ask for what is the maximum area, well then you'd have 720,000 x times y. Let's look at another example. Example, a pizzeria sells pizzas for $13 each. The cost to produce x pizzas is c of x equals 13 minus 11x plus 3x squared. Two parts. Part A, find the revenue from selling x pizzas. Part B, how many pizzas must be sold to maximize profit? Well, part A, find the revenue. The revenue is how much money the pizzeria takes in. Here, the revenue from selling pizzas is how much money the pizzeria takes in from selling X pizzas. Well, some of you may know this from a previous class. If you don't, well, we'll explain it right now. Revenue from selling X pizzas, you sell 10 pizzas, for example, at $13. Well, you sell one pizza for $13. How much money is brought in? $13. You sell 10 pizzas at $13. How much money is brought in? $130. 13 pizzas, or so $13 for each pizza times 10 pizzas. So a general revenue function you can find using a unit conversion argument. Revenue is in dollars. $13 per pizza times the number of pizzas. Pizzas cancel, you're left with dollars. So the revenue is $13 per pizza times X pizzas. Revenue is 13x. Part B. How many pizzas must be sold to maximize profit? Well, we don't have a profit function here, but profit is what we're doing the calculus on. Let's call profit function capital P of x. Profit is what? Well, it's how much money you're left with after you, when you compare what you took in to what you spent. So we took in this much revenue. We spent the cost. The cost to produce those pizzas is that much. How much you take in from pizzas is that much. So we have profit is revenue minus cost. What is that with all these numbers? 13x minus 13 minus 11x plus 3x squared. And what does this equal, just as one polynomial? Negative 3x squared. I always like writing the x squared term first if I can. 13 minus 11 makes a positive 24. And then a negative 13. So here we have a profit function. So we need where its derivative is 0, where it's undefined, and we need to interpret it. P prime, negative 6x plus 24. When does this equal 0? Well, it equals 0. 24 plus 24, or 24 minus 24 is 0, so let's write the right number. I wrote 6 there for the record. 4. 6 times 4 is 24. So we have a candidate for our maximizing value. Why does this give a maximum? Well, I'm again going to use second derivative. Second derivative here is negative. It's negative, which tells us what? The function's concave down, which tells us that the critical point will correspond to a maximum. So x equals 4 gives a maximum. And the question says how many pizzas must be sold to maximize profit, so we need the number of pizzas here. 4 pizzas will maximize profit. Let's look at another example, a couple more. Let's look at 2 more examples, and let's, well, they'll be a little more complicated than these. Show that of all rectangles with a given area, the one with the smallest perimeter is a square. So right here, smallest perimeter, that tells us we're going to be doing calculus on a perimeter function. But of all rectangles with a given area, well, here's a rectangle, sort of a rectangle. There, now it's a rectangle. There's a rectangle with a given area. Well, that means the area is going to be a constant. But in particular, let's say it like this. Our area equals x, y, and I'm going to remark, well, note that a is constant. A is constant. All rectangles with a given area, a is the given value, constant. Show the one with the smallest perimeter is a square. Well, what's the perimeter here? Perimeter is 2x plus 2y. We're going to show that the smallest perimeter is a one with the smallest perimeter is a square. So we're trying to minimize our perimeter function. A function of 2 variables. So let's again eliminate one. In that previous example, there was only one variable with the pizzas. Here we have 2 variables. 2x. Let's eliminate y. Y equals a over x. If y equals a over x, then 2y is 2a over x. And there's our perimeter function. Well, what's p prime? Well, this is one of those examples where having one of those derivative observations does help us. More on that with the second part. Derivative of 2x is 2. Derivative of the next part, negative 2a over x squared. Now why is that? Well, 2a is a constant, and we have 1 over x. Derivative of 1 over x, remember, you could go through a power rule argument, but here I think it's easier to just jump straight through the power rule to negative 1 over x squared. So if derivative of that is that, well, if you put a 2a up there, then you can put a 2a up there, because 2 and a are constants. And we want where this is 0, where it's undefined. This one is our first example where it may be undefined. When does this equal 0? Well, equals 0 when what? 2 equals 2a over x squared. Add 2a over x squared to both sides. 2x squared equals 2a. Multiply by x squared. Get rid of the 2's. x is positive or negative root a. Since this is a rectangle, we're not going to have to worry about the positive, or the negative. So just x equals root a. So that's when it's, when the derivative equals 0. And I'll say, and p prime is undefined when x equals 0. So we technically have we technically have 3 that we would need to consider. The positive root a, the negative root a. Maybe I'll write it like this. We technically have those 3 to consider. But notice, this is a rectangle. If x equals negative root a, well then we have a negative length. So we don't have to worry about that. If x equals 0, well then it's not forming a rectangle. So we don't even have to worry about that. The only one we now have to worry about is x equals the positive square root of a. I don't like how that looks in the positive, so I'm just going to erase that. X equals positive root a. This gives a, I'll write it like this time. This gives a what? Since second derivative. So this tells you you're trying to minimize. So you could just say it gives a minimum. But I'm going to use the second derivative argument and then conclude from that. Second derivative is what? Well, derivative of 2 is 0. How about that other piece? (4a over x cubed). Where did that come from? Well, so going from 1 over x to negative 1 over x squared shows up frequently, so I would recommend doing that enough that you could do it in the one step here. You may want to write this as negative 2x to the negative 2 with power rule, negative 2ax to the negative 2. With power rule, that would give you a negative 2x to the negative 3. Negative 2a times that negative 2 gives you the positive 4a. X to the negative 3 puts the x cubed in the denominator. And this is positive when x equals root a. When x equals root a, it's, what, 4 over root a. I mean, the actual number doesn't matter. What matters is that it is positive. When it's positive, concave up, so it does give a minimum, as the problem said it would. That gives a minimum. Do we answer the question that's asked? Below the smallest perimeter is a square. I don't see anything that says anything about a square. I see that x equals root a, when x equals root a, perimeter will be minimized. Why is it a square? When x equals root a, what does y equal? Well, this will be a square when x equals y. When x equals root a, what is y? Maybe yeah, okay, that's fine. I'll just write it like that. When x equals root a, y also equals root a. Why is that? Well, let x equal root a in your area constraint. You get a equals root a times y. Cancel a root a, you get y equals root a. So y equals root a. So, I'll just say, so it's a square. Where it refers to the one with the smallest perimeter. Because we showed that this gives the smallest perimeter. And then we showed it gives a square. Let's look at one more relatively complicated example. Example. A right circular cylinder is inscribed in a cone with height h and base radius r. Right circular cylinder, meaning the base is a circle and it goes up at a right angle. A right circular cylinder is inscribed in a cone with height h, base radius r. Find the largest possible volume of the cylinder. So here, notice, we are doing calculus on a cylinder, the volume. But to get our formula, we are going to have to jump through a few hoops. Which hoops? Well, let's draw a picture of what we have. There's a cone. A right circular cylinder is inscribed. Well, before even inscribing, the height of the cone is h. So h is that value. The base radius of the cone is r. It may actually be more illustrative to flatten out that bottom. I'll leave it like this. Base radius is r, so halfway across the bottom is r. And we're putting a cylinder in here. Let's draw it a little lower because all of the action is going to go above it. We're also going to put a cylinder in here. Okay. Find the largest possible volume of the cylinder. Well, there's our cylinder. For the volume, we need a couple lengths on it. But, what are our variable quantities here? Well, what is variable is how far up the cone this cylinder is going to go. And because of that, how far in the horizontal direction the cylinder goes will also be variable. So let's call them some variables. I'm going to call this one x and the other one y. I'm going to call this right here x. And I'm going to call this height y. Now why is that? Well, it's because I've done the problem and I know how the variables work out to my liking. But if you did choose the others, if you let them be x versus y flipped around like that, or if you worked with these down here, you would see that your equations wouldn't be set up as conveniently as they could have. Now, why do these work? Well, we'll see in a moment. Why do these work conveniently? We'll see in a moment. But, what are we doing calculus on? We're doing calculus on the volume of a cylinder. What's the volume of a cylinder? Well, remember from last week when we discussed related rates, I mentioned a cylinder, and there's the document cylinder. Volume of a cylinder is the area of the base circle times the height. A cylinder is just a circle extended in another direction. In this case, the perpendicular direction. What is the area of the base circle? Well, the radius is x, so the area is pi x squared. What's the height of the cylinder? Well, it's this length, from here to here, which is all of h without that y. So we have pi x squared times h minus y. Now, our function is of two variables, x and y. H is a constant, remember. H and r are constants. R isn't factored in yet. But h and y are constants. How can we find a relation between x and y? Well, this entire vertical distance is h. I could have drawn it in here. And also, if I flattened that, I guess I'll flatten now. It probably would have jumped out a little more quickly if I flattened it. Yeah, the bottom of this really doesn't matter that much. But the fact that this distance is r does matter. What if I filled this in, the rest of h? And what if you got rid of the cylinder, chopped off half of it? What would you be left with? Well, you would be left with a pair of similar triangles. So what I'm going to do, this is extreme side work, meaning there's going to be a lot of calculus after this and it'll take up some space. But to find a relation between x and y, let's just say we find, as side work, a relation. I'm going to erase this pretty much right after I write it because I'm going to need this board. Between, but this is on video so you can pause and rewind. We find a relation between x and y using similar triangles. What are our variables? R, x, y, h is all of And why are these similar? Well, angle, 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 give, I don't need that there, I need that here. Angle, 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 give similarity. These have that because those lines are parallel. So what relations do we have? Well, we have the ratios of sides are equal. So in particular, y over x equals h over r. So I'm going to take this side, divided by that side, equals this whole side, divided by that whole side. So I'm looking at this smaller triangle, and the sides, you know, I'm next to the right angle. And then I'm looking at the large triangle, and we have y over x equals h over r. So in particular, y equals h over r times x. And that gives us a relation between x and y. H and r, remember, are constant. So what do we have? Replace y with h over r times x. Now, I am going to distribute this just so it's directly a polynomial. Yeah, so there's no product rule to deal with. And I'm always going to put constants out front. Constants generally just get in the way of doing the calculus. So x cubed. So distribute the x squared through, and then I just pull all the constants out front so they're out of the way. Pi h times x squared minus pi h over r times 3 more x's, so times x cubed. And we're doing calculus on this, so we now need the derivative. And where it equals 0, where it's undefined, this one will never be undefined. Where is it 0? Now in this step, before this step, you may want to factor out a pi over h. I'm just going to leave it here. It'll work out fine. 2 pi hx. And again, I always pull constants out front, just so they're really just so they're out of the way. 2x times pi h. Next one, 3 pi h over r times x squared. Derivative here, 3x squared. There's the 3, there's the x squared. And now we want to set this equal to 0. It's never undefined, but we do want to set it equal to 0. Before doing that, I am going to factor it. Now, it may seem a little strange that I factored through here, and now I'm re-factoring in the other direction. But that was to avoid a product rule, and also it's because if you didn't distribute that and you did do the product rule, which you could do, you'd have to make some tedious combination, and I'd rather just do it like this. And I think it's much easier to see. What can we factor from these? Well, I see a pi in both terms. I see an h in both terms. Maybe you don't, maybe my shoulder's in the way. I see a pi in both terms. I see an h in both terms. I see an x in both terms. That's all I see in both terms. What are we left with here? Pull a pi, an h, and an x off, you're left with a2. What are we left with over here? Pull a pi, an h, and an x off, you're left with a 3, a negative. You're left with that r, and you're still left with an x. That's a terrible place. And now we want to set this equal to 0. This will be much easier to set equal to 0 and solve. Equals 0 when what? Well, let's write it over here. Equals 0. I guess I'll write it here. When pi hx equals 0, or when 2 minus 3 over r x equals 0. So set both terms equal to 0. Set that term equal to 0. That term here, divide by pi h. You get x equals 0. What about here? Well, I'll do the side work up here. 2 equals 3 over rx. Add 3 over rx to both sides. Multiply by r. Divide by 3. and you get x equals 2r over 3. Look at all of the work we did. We didn't show what we need to show, and we also didn't show another thing we need to show. What didn't we show? This says find the largest possible volume of the cylinder. It also says find the largest possible volume of the cylinder. So we need to find the volume of the cylinder, and we still need to show it gives a maximum. So why does this give a maximum? Well, again, I'm going to use a second derivative test and show that it's concave down at that point, and then we'll find the volume. So v prime prime equals what? 2 pi h minus 6 pi h over r times x. Why is that? Well, this is just constant times x, so the derivative is the constant. This is an x squared, the derivative is 2x. Combine the 2 and the 3, make the 6, and then there's an x, and the constants flow along with it. So what is v prime prime evaluated at that x value? At 2r over 3. Replace all x's with 2r over 3. That's what you get. What is this? What are all those numbers? Well, first of all, 6 and 3 and 2 make 12 thirds, which is 8, which is not 8, make 12 thirds, which is 4. There's a negative, a 4, a pi, and an h, and look at that, the r's cancel. So we have 2 pi h minus 4 pi h equals negative 2 pi h. Negative 2 pi h is negative, so it's concave down. So x equals 2r over 3 does in fact give a maximum from that observation. And look at all of the work we did. We still didn't answer what the question wanted. The question wants the largest possible volume. We found how we can find the largest possible volume. What is the largest possible volume? Well, we need to substitute that into this v. For the record, I'm leaving this here because after I'm done recording, and I think this is a very nice looking tube. I want a picture of that too for my file of nice letters. Earlier in this video, right over here around where this find is, maybe a little lower, maybe more over here, there was a very nice script F that I drew. And yes, I did get a picture of that for my files. It's a folder with like 20 pictures, maybe 50, I don't know. X equals 2r over 3. What is the maximum volume of the cylinder? Well, replace that in any one of these. I'm going to use, I usually use this one, but I think today I'm going to use this one. Yeah, I'm going to use this one. So I'll say the largest volume is then what? V at 2r over 3 equals, you could use this last equation. I'm going to use this one here, equals pi times 4r squared over 9, squaring all those, times h minus h over r times 2r over 3. What does this equal? Well, it equals, I'm going to put the pi on that now, 4, I guess I usually write the pi's first, don't I? Yeah, I've been writing pi's first. So 4 pi r squared over 9 times what? H minus, what does this equal? Well, the r's cancel. So you're left with h minus 2/3 h. So what does that equal? 4 pi r squared over 9. If you have $1 and you spend 2/3 of $1, you're left with 1/3 of $1. So if you have an h, you get rid of 2/3 of that h, you're left with 1/3 of that h. And this, of course, equals, I guess I have to write it over here, 4 pi r squared h over 27. And then I go back to the notes. 4 pi, oh, I wrote it as 4 pi hr squared over 27. R squared h looks a little better than hr squared, I think. So these optimization problems could get tricky, but notice in this one we still did the same basic thing. We found an equation, we set the derivative equal to 0, we found where it was undefined, we showed it gave a maximum, and then we made sure we answered the question as we did there. In finding the equation, we did have to make a clever similar triangle argument. Now this type of similar triangle argument could also show up in a related rates context, just so you know.